All right, today we're going to talk about a massive problem in the world of AI. What do you do when your AI model, your AI brain, is just too big for the computer chip you're trying to run it on? Well, there's a really clever solution. Let's get into it.
So, just picture this. You've built the most powerful AI imaginable for, say, a self-driving car. It's incredibly accurate, it's amazing, but there's a huge catch. It's so enormous, so demanding, that it just won't fit on a single super-fast chip. This is the exact challenge a team of researchers from the University of Toronto, Carnegie Mellon, and Microsoft decided to tackle.
You see, the best AI models out there right now, especially these things called convolutional neural networks, or CNNs, which are the brains behind computer vision, well, they're absolute beasts. They can spot objects with superhuman accuracy, but they demand a staggering amount of power and memory to do it.
And just how hungry are we talking? Well, a top-tier model like ResNet 152 needs almost 20 times more computation than a smaller one. It's this classic trade-off, right? You want more accuracy, you gotta pay for it with more resources. And that is a huge, huge problem.
So, how do we feed these hungry AIs? Well, every good story needs a hero. And in our story, that hero is a special kind of chip called an FPGA. That stands for Field Programmable Gate Array. The easiest way to think about it is like a piece of hardware clay that you can mold into the perfect custom tool for whatever job you need.
So how do these FPGAs stack up against the CPUs and GPUs we all know? Well, CPUs and GPUs are kind of like a Swiss Army knife. They're general purpose. An FPGA, on the other hand, can be programmed to become a highly specialized tool for one specific task, like running a neural network. They're incredibly power efficient, and you can customize them on the fly. The researchers in this paper use this cutting-edge FPGA accelerator called HPIPE, and its superpower is that it doesn't just run the AI model, it actually builds a unique, perfectly optimized piece of hardware for every single layer of that model. It's the absolute ultimate in custom-tailored hardware. And you can see just how powerful that is. For a model like ResNet 50, a single FPGA running HPIPE gets 3.7 times the throughput of a top-of-the-line NVIDIA V100 GPU. I mean, that's a seriously impressive piece of tech.
But even our hero has an Achilles heel. HPIPE's incredible performance comes with one very strict rule. And if you break that rule, the whole system just stops working.
So here's the catch. To get those blazing fast speeds, HPIPE has to keep all of the AI model's parameters, all its weights, stored directly on the chip's own memory. Now, that's totally fine for smaller models, but for the giant, high-accuracy models we really want to run, it's a complete deal-breaker.
And just look at this. A popular model like MobileNet fits on one FPGA, no problem. But the bigger, more accurate ResNet models, they just don't. A sparse version of ResNet 50 needs at least 2 chips. ResNet 101 needs 4. And the massive ResNet 152? It needs a minimum of 6 FPGAs. So you can't even use HPIPE unless you solve this problem.
So, if you can't fit the whole brain in one box, the logical answer is to find a really smart way to split it across multiple boxes that all work together. This is called partitioning, and this is where the real innovation in this paper starts. Now, people have tried to solve this partitioning puzzle before, but the old methods were all kind of flawed. Some were super powerful but incredibly slow, taking almost 20 minutes for a simple network. Others were fast but, kind of clumsy. They'd create these inefficient splits that just wasted the hardware's potential. What they needed was something that was both smart and fast.
And that brings us to the secret sauce of this whole research paper. The team noticed something really fundamental about the structure of most neural networks, and that insight allowed them to create a brilliant and incredibly fast new way to do partitioning.
It turns out a neural network's resource needs are what you'd call U-shaped. The early layers of the network, they need tons of computation, but not a lot of memory. But the later layers are the complete opposite. They need huge amounts of memory. So a simple straight-line split just doesn't really work well with this kind of imbalance.
So their algorithm solves this like a really clever puzzle. First, it tries a simple greedy forward approach. But nope, it gets stuck pretty quick when a big memory-hungry piece won't fit. So then, it tries a bidirectional approach, packing those memory-heavy layers from the end of the network onto the first chip. That helps, but it still gets stuck. The final brilliant move is what they call the mover. It intelligently shifts a small piece from the first chip over to the second one, creating just enough space to solve the puzzle perfectly. It's kind of like playing Tetris, but for an AI brain.
And the result of all that cleverness? An algorithm that finds this perfect, complex solution not in minutes or hours, but in just 3 to 7 seconds. It's unbelievably fast and incredibly effective.
Okay, so that's all great in theory. But the real question is, does this clever software trick actually translate into real-world performance? Let's take a look at the hardware results.
For the MobileNet V1 model, the results are just stunning. When they double the hardware from 1 FPGA to 2, they get a perfect 2x performance increase. This is what engineers call linear scaling, and it's basically the holy grail of parallel computing. Double the hardware, double the speed.
And even with the much larger ResNet 50 model, the results are almost just as good. Doubling the FPGAs from 2 to 4 gives them a 1.8x performance boost. That is remarkably close to a perfect speedup.
The big takeaway here is simple. Their partitioning method works. It actually works. You can throw more hardware at the problem, and you get an almost perfectly proportional increase in speed. For this kind of accelerator, that just wasn't possible before.
And check out how this stacks up against other systems. For ResNet 50, they're getting 4 times the throughput of a competing system while using way fewer chips. But for the absolutely massive ResNet 152, the difference is just staggering. They outperform a 16 FPGA system by over 170 times. The performance here is it's in a completely different league.
Okay, so let's wrap this up. What is the crucial point here? What's the big idea we should all take away from this?
Well, this research really matters because it unlocks the ability to use the biggest, most accurate AI models on this super efficient FPGA hardware. Their automated process is lightning fast, it achieves near-perfect performance scaling, and it makes FPGAs a much more powerful and viable tool for things like autonomous driving and other demanding real-time AI.
But maybe the most powerful idea is this one, and it's taken right from the paper itself. Their smart software partitioning basically creates a single, giant, virtual FPGA, a superchip that is physically impossible to build today. They figured out how to make a team of small chips act like one impossible giant. And that, well, that is a truly game-changing idea.